So we just finished the first part of this problem, the 2D collision, where they are sticking together, and we found the final velocity after the collision of the new object that was formed. Now the second question is, what is the impulse felt by each individual ball? And in order for us to answer this question, we need to remember that the impulse, J, is equal to the change in momentum. So we have momentum information. We didn't necessarily find the change in momentum of each ball, but we can, thinking about how this new object still contains object 1 and object 2. Even though they're together, we can still treat them as two individual objects. So we're going to have to calculate the change in momentum in order to answer this question. And the thing is, we are still going to have to be thinking about our components, right? So the impulse in the x direction is going to be equal to the change in impulse of the x direction. So let's set that up down here. And I'm still, right, we're on this new question. So we're still in the x, but more specifically, we're going to be talking about each individual object. So for the x direction, we have ball 1 and we have ball 2, okay? So we need to be thinking about how to calculate the change in momentum of these objects in this x direction. So we want to find the change in momentum of the x direction for this object 1. So that means we need to know the mass of object 1 and the velocity final in the x direction, and subtract that from the velocity final, or velocity initial in the x direction. Okay, so we are still talking about components. And again, when you're looking at this object, yes, I know it's one individual object, but it's comprised of the mass of object 1 and the mass of object 2, so we can think about how this second object still has, you know, a part of it that is 2 kilograms and a part of it that is 6 kilograms. And we're going to utilize the information we found in this last problem. So if we're going to find the change in the momentum of the x direction for object 1, the mass of object 1 is 2 kilograms. The final velocity in the x direction, we can see it here, is this, right? So this new object, both the first object and the second object have an x velocity of 0.75. So we're going to go ahead and use that. And its initial velocity in the x direction here was 3 meters per second. Okay, so we can do that. And 0.75 minus 3 times 2. Okay, the change in momentum for the first object in the x direction is negative 4.5. I'm going to go with Newton seconds because that's impulse. You can do kilograms, meters per second, up to you. But this object slowed down in the x direction, so that's why it has a negative impulse. Remember, having a negative impulse does not imply it is moving in the opposite direction. It just means that it is slowing down. It changed it in the opposite direction, in this case, of where it was moving. So we can do, so that's the x information. Let's stick with object 1, and we'll talk about the y information for it, okay? So the delta P in the y direction of this first object is going to be its mass times Vfy minus V naught y. So again, the mass is 2 kilograms. Final velocity y, again, we calculated that in the last problem, was 3 meters per second. Right, because our final object had that mass, or that velocity, and so the 2 kilogram mass is now moving at 3 meters per second. And recall that this object is not moving in the y direction, so it had the 0 velocity in the y. So delta Py is going to be positive 6 Newton seconds. Okay, so we can come and talk about the total momentum, or change in momentum. This first object had an impulse going back, right, to the left, 4.5, Newton seconds, and up 6 Newton seconds. So its change in momentum, otherwise known as its impulse. And right, I didn't actually write negative 4.5 there because by putting the vector to the left, that implies the negative, so you don't need to write the negative. But we are going to do Pythagorean theorem to find the square root of 6 squared plus 4.5 squared. So we get an impulse of 7.5 Newton seconds. And again, we need to find the angle, so we can go ahead and use tangent. I'm not writing this out because we have similar work up there, and we're getting used to using our trigonometry functions to do this. So we're going to do tangent of 6 because that's the opposite over the adjacent 4.5. And I get an angle of 53.1 degrees. Okay, so the impulse of object 1 is 7.5 Newton seconds. Now, if I'm using that 53, I can't just say at 53.1 because 53.1 implies up here, and that's not where we are. We're in the second quadrant. So there's a few ways that you can talk about this angle. You can figure out where you are in relation to 0, find this angle, or you can say 53.1 degrees up from west. That's the same thing, so that's what I'm going to do because here's the west direction. The 4.5 newtons is going out west, and then I go 53.1 degrees up. Okay, so 75 at 53.1 degrees up from west. Okay, now we're going to do the same thing for our second object. And our second object here, we can do the x information. Delta px is equal to mass 2 times vfx minus v naught x. And our mass for object 2 was 6 kilograms. Final velocity x, remember this 0.75 is also the velocity of object 2. So we have 0.75. It was not moving in the x direction, so this would be a 0 here. So delta px for this second object is, what is that, 4.5, I think, times 0.75, yep, 4.5 Newton seconds. Okay, and that's positive. Do it for our y direction, so delta py is equal to m2 vfy minus v naught y. So 6 vfy, remember, right, that what we calculated is it. So we got 3 minus all of its velocity was in the y direction, so that would be 4. So delta py, 6 times 1. And this is times negative 1 because 3 minus 4 is negative 1, negative 6 Newton seconds. Now, what if you notice, right, there's a connection between the change in momentums of these two objects. They are equal but opposite, which is kind of cool because that's Newton's third law, right? Every action has an equal opposite reaction, every force has an equal opposite force. And then because the force is happening over the same time in the collision, every impulse has an equal and opposite impulse. Okay, so if we draw this second triangle, right, we are going to the right 4.5 Newton seconds, and we are going down, sorry, I wrote that on the wrong side. Let's go 4.5 Newton seconds, and if we go down, right, this is 6 Newton seconds. So these triangles are related to each other, right? If we go and do the same math, right? 6 squared plus 4.5 squared, square root of it, that would get me 0.75, or, well, 7.5. And if I found this angle here, my opposite side is still 6 and my adjacent side is still 4.5, I would get the same exact angle, okay? Now, if you put these two triangles together, imagine, well, actually, let me move this real quick. if we put these two triangles together, they are opposite of each other, right? 180 degrees away from each other, which in a 360-degree world, that is the opposite direction, okay? So every time we get this collision, Newton's, even in 2 dimensions, 3 dimensions, you are going to see this equal and opposite. So you don't have to calculate both of these, because we know if we are right and our work is right, then we should be getting equal but opposite impulses. And if we don't, then you know something went wrong in your work. But in the end, if you calculate one impulse, then you know the other impulse is the same magnitude, but in the opposite 180 degrees direction. So we have 7.5 Newton seconds at 53.1 degrees. Technically it's negative 51.3 because you're going in the opposite direction, but you can say down from east. Right? Up from west, down from east, those are opposite of each other. So that's a cool, we still see this connection between Newton's third law, even in 2 dimensions. So hope this helps, and give your homework a try.